Welcome to OOkul. I welcome you all to this lecture series of basic thermodynamics. This is lecture number 13, that is the properties of pure substance. In the previous lecture, lecture 12, we understood the concepts related to availability, irreversibility, exergy and all. Okay, so in this video we will be discussing about the properties of pure substance. So let us begin. So basically this is a TS diagram, typical TS diagram. Let us see different regions into this one. First of all, this is a liquid region, this is a vapor region, and this one is a liquid plus vapor region. This is a critical point. So this region is also known as a subcooled region. This region is also known as a superheated region, and this region is also known as wet region. Okay, then this is one line at pressure P1, this is another line at pressure P2, and we consider P2 greater than P1. Okay, so this is the curve for saturated liquid, and this one is the curve for saturated vapor. Okay, this is denoted by generally by F, and this is denoted by G. And then there are some lines which originate from the critical point. They are known as the dryness fraction lines. Okay, this way it is. So what is all this? We will discuss one by one. So these dotted lines are dryness fraction curves, okay, having the value of dryness fraction 0 at this one, x equal to 0, and it keep on increasing, and here at this x becomes equal to 1. Okay, so first of all let us see what are those different terms. First of all, we see a subcooled region. It is the region where the substance is below its saturation temperature at the corresponding pressure. Now see this T saturation is the saturation temperature corresponding to this pressure P1. So if any substance which is at a pressure P1 is below the temperature T sat, that is T saturation, will be in the subcooled region, will be in this curve, will be in this zone, and will be in the subcooled region. Okay, so we define degree of subcooling as, suppose we talk about this substance having the temperature as T1. Since at pressure P1 T saturation is this curve and this temperature T1 is below the T saturation, that means it's in the subcooled region. So the degree of subcooling is given by T sat minus T1. Okay, similarly for the superheated region, it is a region where the vapor is above its saturation temperature at the corresponding pressure. Now see, suppose at this same pressure P1, the substance is having the temperature as T2, and this T2 is greater than the T saturation. Okay, so the substance is at this point, this is the state of the substance, so it is said to be in a superheated region or superheated state, and the degree of superheat will be T2 minus T saturation. At how much higher temperature the substance is above its saturation temperature. So that is known as degree of superheated. That is T2 minus T set. Okay. Then the third region, the wet region, it is the region where saturated liquid and saturated vapor exist in equilibrium, because you can see the middle portion within the dome is known as the wet region. Here both liquid and vapor exist in equilibrium. Okay. Near to this saturated liquid curve, liquid will be more, the portion of liquid will be more. It will keep on converting to vapor, and as we reach the saturated vapor curve, all the liquid has been converted into vapor. Okay. So the middle region within the dome is known as the wet region. Now we see dryness fraction. So in the saturated liquid vapor mixture, that is in the wet region, the mass fraction of vapor is called the dryness fraction, and it is also known as quality. Okay. And it is expressed as denoted by X equal to mass of vapor over mass total. So mass of vapor remains as it is. Mass total can be written as mass of vapor plus mass of liquid. Okay. So simply mv over mv plus ml. This is the dryness fraction. Now let us take total volume as volume of liquid plus volume of vapor. Okay. So this is V multiplied by specific volume of vapor plus specific volume of liquid, which is equal to ml into VL plus mv into VV. Dividing this whole equation by mv plus ml, we get V equal to ml over ml plus mv into VL plus mv over ml plus mv into VV. Okay, so this term is your dryness fraction, and this will be 1 minus dryness fraction. Okay, so you can write it V equal to 1 minus X into Vf plus X times of Vg. Since this is the volume of liquid, so it can be written as Vf, and this is the volume of vapor, so this can be written as Vg. Okay, so this is only written here. So now just arranging the terms, we get V equal to Vf plus X times Vg minus Vf, and this is V equal to Vf plus X times of Vfg. Vfg is nothing but Vg minus Vf. Okay, so this is for the volume we have calculated. For the other quantities such as enthalpy, internal energy, entropy, similar relations holds. That is H equal to Hf plus X Hfg, U equal to Uf plus X Ufg, S equal to Sf plus X Sfg. Okay, but please remember that rho, that is about the density, rho is equal to rho f plus rho x rho fg is not applicable. Okay, it is not applicable, but it is applicable as 1 by rho equal to 1 by rho f plus x times of 1 by rho fg is applicable. Okay, because this density is nothing but the reciprocal of specific volume. Okay, so that's why that relation becomes reciprocal. Next is, we see what is a critical point. Now you see, in this case, let us go back to the diagram once. See this, as you can see, when the pressure keep on increasing, okay, this curve is shifting upwards. So when the pressure increases up to that much point, that the latent heat of vaporization, basically this region from here till here is the latent heat of vaporization. Okay, you know what is latent heat of vaporization? It is that heat which is required for the conversion of liquid into vapor. Okay, so as the pressure is increasing, you can see the difference between the saturated liquid curve and saturated vapor curve is decreasing. That means the enthalpy of vaporization or the latent heat of vaporization is decreasing. Okay, and as we go on further increasing the pressure, we will reach at such a position that the enthalpy of vaporization will decrease so much that without the conversion of liquid into the mixture, directly it will flash into vapor. Okay, because in all other cases, what happens, first of all, there is a complete liquid, then it starts converting into vapor where the liquid and vapor exist in equilibrium in the wet region, and then all the liquids get converted into vapor gradually, okay, and reach the superheated region. But as we keep on increasing the pressure, we will reach at such a state or such a position when the latent heat of vaporization will reduce to such an extent that there will not be any requirement of any heat or any enthalpy for the conversion of liquid into vapor, but it will directly flash into vapor. Okay, so at that point is known as critical point. Okay, see, it says as the pressure increases, latent heat of vaporization decreases and it becomes zero at critical point. At critical point, substance directly flashes into vapor. Okay, that means the process of conversion of liquid into vapor does not take place gradually, but it directly flashes. Okay, so the dryness fraction at critical point is not defined. Please remember this, that the dryness fraction at critical point is not defined. Okay, then only one phase exists at critical point and it is neither liquid nor vapor. Please remember that. Okay, only one phase exists and it is neither liquid nor vapor. So critical point is a fixed point and degree of freedom is equal to 0. Okay, degree of freedom is equal to 0. Please remember this. Okay, now we see the enthalpies at various points. We have different points 1, 2 and 3. Okay, so beginning with 3 lies in the wet region. Okay, so for the wet region we have H3 equal to HF plus X HFG. We have seen this expression, how it is derived. It is similar to the case of a specific volume, where HFG is the latent heat of vaporization. So please remember, within the wet region, always you have to calculate the enthalpy like this. That is H3 equal to HF plus X times of HFG, where this is the dryness fraction at 3. This is the dryness fraction at 3. Okay, superheated region is dH equal to Cp dt, the basic definition of enthalpy. So superheated region we will have H2 minus Hg equal to Cp vapor T2 minus Tsat, that is saturation temperature, or H2 can also be written as Hg plus Cp vapor T2 minus Tsat. Okay, then in the subcooled region again we have dH equal to Cp dt. So HF minus H1 equal to Cp T saturation minus T1, because T saturation will be higher than T1, or H1 will be equal to HF minus Cp liquid, because this will be liquid because we are talking about the subcooled region. So this will be liquid into T saturation minus T1. Okay, from the basic definition of enthalpy we have H is equal to the summation of internal energy plus flow work. Okay, this is known as flow work. So for liquids, specific volume is very small, and if pressure is also small, then PV can be neglected. Okay, so for the liquids generally we have the values of enthalpies very close to internal energy under these conditions. That is, the pressure is small, so at those small pressures we have the values of enthalpies and internal energy is almost same. Next we see the entropy at various points. The 3 points remains the same, that is, the point 3 lies in the wet region, point 1 lies in the subcooled region, and point 2 lies on the superheated region. Okay, so for the wet region we have S3 equal to SF plus X times SFG. We know from the basic definition of entropy that ds equal to del Q by T. Okay, and this del Q in the wet region is the latent heat of vaporization divided by T. So latent heat of vaporization written as HFG over T. So this is the difference in the wet region, that is entropy at gaseous state or vapor state minus the entropy at liquid state. So Hg minus SF equal to latent heat of vaporization, that is HFG, divided by T saturation, because in the wet region that temperature will be the T saturation, the saturation temperature at which the conversion of liquid into vapor takes place. Next is, in the superheated region we have ds equal to del Q by T, given as this del Q written as Cp dt by T. So S2 minus Sg will be equal to, since we are in the superheated region, so it will be Cp of vapor, and if we integrate it we get natural log T2 by T saturation. Similarly, in the subcooled region we have ds equal to del Q by T equal to Cp dt by T. So SF minus S1 equal to Cp liquid natural log of T saturation by T1, since in this case T2 is greater than T saturation, and in this case T saturation is greater than T1. Next is we talk about the reference state in steam table. So internal energy equal to 0 and entropy equal to 0 at triple point of water for saturated liquid. This is the reference state. At this point, H equal to U plus PV. So U already taken as 0. So H, which becomes equal to PV, is slightly positive. Okay. In the wet region, you can say that pressure and temperature are dependent properties because in the wet region, the pressure and temperature curves overlap. Okay. Next is, that was the TS diagram. Now let us see another diagram. This is the T versus S, V, U and H. All those looks very similar. So now let us define the regions into this one. This region is the solid region. This one is solid plus liquid. This one is liquid. And we have this region as vapor. So between solid and liquid we have solid plus liquid. Between liquid plus vapor we have liquid plus vapor. And between solid and vapor we have solid plus vapor. Okay, and this line is known as the triple point line. Triple point means that condition at which all the three states or three phases of water or any substance, say the solid phase, the liquid phase and the vapor phase, coexist. So that is known as the triple point condition. So this is the triple point line. Please remember that in the TS curve, TV curve, TU curve, TH curve, whatever sort of curve we talk about, we have the triple point as a line. Next we see the PT curve. Okay, PT curve, that is the pressure temperature curve. So in this is the solid region, this is your liquid region, and beyond this is the vapor region. Okay, so please remember one thing, that in a PT curve the triple point is a point. Okay, in the previous case I have shown you that it was a line, but in this case it's a point. Okay, and this top point in this case is a critical point. Okay, this is a critical point. Okay, so this is about the PT curve. Now see, this is written here that out of the properties V, P, T, U, H and S, that is specific volume, pressure, temperature, internal energy, enthalpy and entropy, if the graph is made between P and T, that is pressure and temperature, then phase change region will be absent, because in this you can say that there is no phase change region and triple point will be a point. Okay, and if the region is not PT, that is there is any other curve, that is then the pressure temperature, then the phase change region will be present and the triple point will be a line. So please remember this. And critical point is a point on every diagram, whether it's any sort of curve, the critical point always remains a point. Okay, now we talk something further, that for the general substance, when we go from solid to liquid, it expands, whereas when we go from liquid to solid, it contracts. But for water, it's a different case. When we go from solid to liquid, it contracts. When we go from liquid to solid, it expands. Okay, so there is a very important real life example of this one that we come to here sometimes in the colder regions, in the very cold regions where the temperature falls to minus in the sub-zero region. We come to hear that sometimes the supply lines of water get burst. Why? Because in that case what happens, the liquid water gets converted into solid in the form of ice, and we see here that water, when gets converted from liquid to solid, it expands. So within the pipeline, when the water gets converted into ice, the liquid water, it expands and the pipeline gets burst. Okay, so that is the very common and very basic real life example of this thing. Okay, so now we will see this on a PT curve. Okay, so on a PT curve, when we see this is the triple point. Okay, first of all, let me write the regions. This is the solid region, this is the vapor region, and this one is the liquid region. Okay, and this one will be a critical point. So this is the fusion curve, you can say the fusion curve for any general substance. This is the fusion curve for general substances, and this one is the fusion curve for water. Just see the difference, the slopes and all. The slope, that is del P by del T, that is the slope of the fusion curve for any general substance is greater than 0. You can see the slope, and the slope of the fusion curve for water, that is H2O, is less than 0. Okay, so please remember this, that is the slope of the fusion curve for general substance is positive, whereas for water it is negative. Why it is, we have already discussed. Now let us see the PV curve. So the PV curve, again let us define the regions. In this, the line goes like this. Okay, it starts this way and goes. So this is the liquid region, the vapor region. So this region becomes the liquid plus vapor, the liquid plus vapor. So this is any temperature, the constant temperature curve. It is like this, that it comes this way straight and then falls here. And this is the T at critical temperature. Okay, so this is the sort of the PV diagram. Just remember in this thing, that is the saturated liquid curve is a bit steeper and the saturated vapor curve is less steeper. Okay, this is more steeper and this one is less steeper. The saturated vapor curve is less steeper and saturated liquid curve is more steeper. Now let us see the another diagram that is known as the HS diagram, and this HS diagram is also known as Moliere diagram. Okay, this is known as Moliere diagram. So in this, the regions are, this is the liquid region, this one is vapor region, and this is liquid plus vapor. This one is liquid plus vapor region. So this is pressure P1, pressure P2, and we say that pressure P2 is greater than P1. This is temperature T1, this is temperature T2. Okay, so it goes like this. This is T2 and this is T1. Okay, so in the wet region, that is liquid plus vapor region, we can see that these two lines corresponding to, you can say, either pressure P1 and P2 or temperature T1 and T2, both the thing is same, because in the wet region the pressure and temperature curves coincide, so they are parallel. But in the vapor region or in the superheated region also, you can say that the pressure curves slopes upwards, whereas the temperature curve slopes downwards. Okay, so there is a difference in the vapor region or in the superheated region, but in the wet region both the curves, that is pressure curves and temperature curves, coincide. Next we see this thing, that is from the second TdS equation we have TdS equal to dH minus VdP, and as in this case the pressure is constant, so dP becomes equal to 0. So TdS equal to dH or dH by ds gives you temperature. Okay, this we are talking about in the wet region. Okay, or for a particular, basically you can say for a particular temperature pressure. So this HS diagram is known as Moliere diagram, I have already told you, and it is used in the power plant analysis. Constant pressure curves are straight lines in wet region and the curves of increasing slope in the superheated region. I have already shown you. Constant pressure curves diverge in the superheated region. Okay, this also I have told you. So that's all for this class. I hope you are enjoying learning with us. So in the next video, we will be coming up with another topic of thermodynamic relations. Till then, keep learning with us, keep sharing the videos with your friends and colleagues so that also they can also get benefit out of it. And if you have any doubts, any comments, any suggestions, any queries, you can write to us in the comment section below. And also you can also connect with us on our Facebook page, Twitter, and you can also contact us through the email. So see you in the next video. Till then, thank you and have a nice day.